Hello, welcome everyone to the fourth installment of Proto-Talks. I'm your host, Matt Morgan, president of Proto-Getic, the predictive design marketplace. Before we begin the talk, I'd like to say a big shout out to our sponsor today, Habersham Metal Products, a manufacturer of high quality security products. Thank you, Habersham. Today's approximately hour-long conversation features an in-depth deep dive into blast, the anatomy of an explosion. I know this topic is going to be very interesting and get us all thinking and rethinking perhaps in a different way. To that end, though, I would like to welcome back Holly Stone from Stone Security Engineering. The response to her State of the Industry talk in August was just incredible, and we knew she had some more to say, so we were very excited to have her here. With more than 30 years of experience in engineering, blast, anti-terrorism, and emergency response, Holly really has dedicated her career to protecting people, buildings, and critical infrastructure. Her portfolio of work includes, and I want to get this right, so bear with me for a second, includes multi-hazard vulnerability assessments, new protective designs for the U.S. Departments of State, Justice, Defense, and Homeland Security, as well as national universities, chemical plants, oil refineries, Fortune 50 companies, and international NGOs in what we can only describe as hostile environment locations. Somewhere in there, she also founded Stone Security Engineering, so apparently she doesn't sleep. Welcome, Holly. Welcome back.
Thanks, Matt. I really appreciate that. So anybody who knows me knows that I love to talk about what I do. Oops, sorry. There we go. Knows that I love to talk about what I do, and I really appreciate the opportunity to share this with you, because I do think it's interesting information. You know, as you look at the world around us, explosions are happening on a regular basis. We're very fortunate that not so much in the United States, but they have occurred here, and they're definitely occurring around the world. So I wanted to share with you some basics about explosions. And generally speaking, I'll be talking about sort of explosion characteristics. What determines the magnitude or the load of the explosion onto a structure or facility. Very briefly go over explosive types, and then talk about the consequences of explosions. And then I'm going to end on 7 easy actions that you can take to increase the safety of your people. And so I'm going to start with what's the difference between an explosion and sort of an everyday wind load or snow load or just gravity loads? And there's 2 real main factors. One is that it's the magnitude. Explosions can go up to 10s, 20, 30,000 pounds per square inch, or PSI. That's the pressure. And also they happen like that. They happen in milliseconds instead of seconds. And that allows us to take a dynamic analysis approach to designing a building, and we don't have to put the load on it for very long. It's just that it hits the load and it's gone. So that millisecond is what really allows us to design for these very large loads. So what is an explosion? An explosion is a rapid release of energy in the form of light, heat, sound, and a shock wave. And for our purposes today, and in general for blast resistant design, it's that shock wave that we really focus on. Then there's some characteristics about it that we have to know when we make decisions about how to design a building, where to site a building, you know, where we have to reduce access so that the threats don't get too close. The explosion expands outwards in all directions. It has extremely high loads, as I was talking about, but again, that's extremely short duration. It decreases exponentially with distance. So there's a word called standoff we'll talk about, but that's very critical in when you're working on these types of projects. And then also you have to think about the orientation of the structure or the column or the wall to where the blast is. So I'm going to go into those a little more detail. And this animation, I'm going to talk you through it. It shows some of these characteristics. So we're doing a cut section so you can see what's happening. I'm going to play it once for you to see. And then I'm going to play it one more time and then we can talk about it. So it rapidly, it expands in all directions. So you can see the bubble that's going out. When it gets into the building, it pushes up and it pushes down. So it expands in all directions. And that means that a floor slab, for instance, is being loaded in the direction that floor slabs are generally not designed for. So one of the things that we look at when we're doing design is how the blast loads are affecting the floor slabs or other horizontal surfaces. And then also, I want to show one more time. So as it goes over, you can see that the animation is showing that it goes over the roof and then it comes down the back and around to the sides of the building. And that's really important to understand and to acknowledge that just because you can't see the explosion or the explosion can't see you doesn't mean you won't have load, you won't have pressure on you. So I'm going to talk a little bit more about that later, but this is sort of the general concept there. I think I have two graphs. This is the first one, so promise not too bad. This is what we call a load signature. The only things that I want to show you on this is time, and this is magnitude of pressure. So the first thing that happens, the explosion happens, and then there's a short period where whatever you're designing or looking at hasn't gotten the load yet. So when it gets to that location, it's the time of arrival. What happens is there's almost an immediate increase in the pressure to what's called the maximum peak pressure. And then it degrades very, very quickly. This where it crosses here is where that positive push ends and where the vacuum that's around it kind of starts pulling things back. But we're really just going to be looking at this positive push right now. And the time from the max pressure to going back to zero over ambient is called the duration, or TD. So those are words that if you talk to people who are looking at design, they'll be using those types of words. I may use a little bit of it, but I just want to make sure that you sort of understand those very basic things. The other is, what determines the magnitude of the loads, and it's charge, weight, and type. So how much and what type are we looking at? What composition? Standoff distance, we're looking at the angle of incidence, and confinement and shielding. So I'm going to walk you through those now. So first thing is how much TNT equivalent, and I'll talk more about that, but that's what we think of when we think of design, is how much TNT equivalent can actually be delivered and where can it be delivered to. So it depends on, is it the size of the threat? So if you have a car or an SUV or small moving, you can see increasingly large quantities of explosives that can fit into those types of vehicles. But also you can have a pipe bomb. You can have a backpack bomb, as it were. And what I'm showing you right now is it's termed the DOJ or Homeland Security bomb threat standoff chart. And this is used by first responders to think through what evacuation distances they need to do. So if they have a pipe bombs generally are 5 pounds, give or take. And if you're in a building, you want to be 70 feet away, and they want to keep people who are not in buildings 1,200 feet away, because that building is theoretically protecting people. One other thing I want to point out in this is, they say a car bomb can only hold 500 pounds. If you're in locations where there's not very strong law enforcement, where it's very easy to get explosives, you can see a car with more than 500 pounds, but it rides low. And it's pretty obvious something's going on with that vehicle. And those are the types of things you'd see in Afghanistan and other hostile environments. So there's different types of explosives. There's ANFO, which is ammonium nitrate fuel oil. This is a picture of C4. This is some det cord, which is often used in conjunction with C4 to do testing or to do an attack. But from a design perspective, we bring it all back to what we call a TNT equivalence. And so we call TNT an equivalence as one. So if you have ANFO, which has less energetic release capacity, they have a multiplier at less than 1. So for instance, it would be 0.8. So if you have 100 pounds of ANFO, the TNT equivalence would be 0.8 times that. C4 tends to have a greater energetic capacity than TNT, so it would be a 1.2 or 1.3 factor. But when you're talking to people about doing design or assessments, they'll always bring it back to that TNT equivalence. So even if you tell them we think it's an ANFO type threat, we'll still do all the analysis and the discussion sort of from that TNT equivalence, because that's what most of these designs do. So it gives a common ground when you're comparing different types of information. So the second thing is standoff. And a standoff is the distance from the explosion to whatever you are interested in. So the distance from the explosion to the face of a building, the distance from it to maybe a 3rd-story column, 4th-story column, the distance from a backpack to a column or something like that. That's all called standoff distance. And standoff is critical because the load from an explosion decreases exponentially with distance. And as an example here, and it's metric because I wanted to be inclusive. So for this particular threat size, you would get at a 1.5 meter standoff, you would get an extremely large pressure and impulse, so pressure on it. So that push that's being on it is extremely large. If you take it, move it by 4.5, 5 meters, it takes it from 137,000 kPa down to 9,000 kPa. And then you can see as you go further and further, it gets very low. These are not, even down here, they're not small blast loads, but they are significantly less than you have right here. So one of the things is A, standoff is really good. B, distance matters even more when it's a close in, when you're closer to your target, as it were. So standoff is good. So there's different ways of talking about standoff distances, and they have to do with how the load will affect the structure. The first is close in or contact. And those instances, when you have that type of threat, for instance, the concrete wall that you're looking at doesn't actually have time to bend or flex. So it's actually breaking the material itself. And I have some photos and a video to show you that. But that close in is actually affecting the material properties as opposed to after something bends, then it breaks after it bends. Near field so far field is where you have a distributed load. So I have a column and I have a far field explosion. And as that shock wave comes over, it's going to give a uniform load across the front, essentially. When you're in near field, so you're kind of, not close in, not too far, but it's enough that you will have more load at the bottom of a column than you will at the top. And all of that is important from a design perspective, from a siting perspective, things that you can do to better protect even before you start hardening a building. So this is close in. These are some photos from some demonstrations that we've done at our blast test facility. These are from a class that we taught, and we set up a series of different sized of panels, and they're all the same thickness. The charges are all the same size, but they're loaded at different distances from the face of the panel itself. So you can see here in the upper right corner, that little baggie, which is where the explosives are located, is, I think that's 6 to 12 inches. I can't tell from here, from the face. And we did this series, and we had contact, and then we had, I think, 6 inches, 18, and 24, or something along those lines, because we wanted to see the difference in what the effect is on the panels. And this one to the top left here, it was, I think it's a nice descriptive photo of, if you have a piece of luggage that's set against a wall, what is it going to do? So this is the actual test video of the explosion. So you can see with that, we tested 6 different panels. Oops, it keeps going. And these are some of the post-explosion, post-test or demonstration photos. This one down here on the left is from that suitcase being put directly against the panel. This one here was contact to just a few inches away, and you can see the panel is gone. It's completely pulverized. It's completely breached. And then this one, actually, these two, as it turns out, are different views of the same one. That is a little further out, and it was able to shear, it was able to fracture the panel itself. And then this one here is where the charge was farther away. It had a very localized effect, but it didn't completely pulverize. So this is the front view of that, and then this is the back view of that. So we have a breach, and then also spall, which is portions of the concrete, in this case, spalling off the back and becoming projectiles. So this is a really good thing to think about when you're looking at lobby areas, when you're looking at places that perhaps don't have access control. Close-in effects are really important. So the other thing, another characteristic is the orientation. And so the two extremes of orientation we call reflected or side-on. And the way I like to think about that from a sort of basic thought process is think of the building as a seawall, and think of the shock wave coming across the land. Think of that as the ocean, the waves coming in. So when your seawall is perpendicular at a 90-degree angle to those waves that are coming in, you get this crashing. You see energy being released in the form of spray, of noise, and then you also see that that when it hits the wall, it starts reflecting back, and so then it starts to also hit the next portion that's coming in. So it's sort of a little bit of back and forth. So the magnitude of a reflected, a 90-degree, is going to be the biggest magnitude that you see. When you look at a side-on, and side-on can refer to the sides of the building, what's happening on the roof, what's happening on the backside of the building, and in some instances, some of the buildings further on. And the side-on, thinking of the same thing as that seawall, is that now the ocean waves are coming parallel. They're moving parallel to that seawall. There's still energy being transferred. There's still energy being released, but it's significantly smaller. You can hear the lapping of the waves. You can see some turbulence in the sea, the ocean as it goes by, but it's nothing like you saw when it was coming perpendicular. So I think that's the way I can visualize it, and I found it's been helpful for a lot of people. But what you also need to know is there's different angles between those two, and it reduces as the angle becomes more acute as you get to the from perpendicular to parallel. And so again, you think that helps you think about where you site your actual building. So also we think about the angle of incidence, and the angle of incidence is basically, if this is your wall, angle of incidence, what we're just talking about, it's perpendicular, but then as you go up, it gets closer and closer to parallel. And so that with high rises or very long, low-rise buildings, the pressure actually won't be evenly distributed over the face of those structures. So on the right here is just a graphic representation. The red is the largest load. We're seeing concentric arcs because again, it's like a balloon. It's going out in concentric circles. But that the blue is very small at the top and it's very high at the bottom, and it decreases for two reasons. One is the angle of incidence, but also actually the distance is increasing as well. So your standoff is increasing and your angle of incidence is changing. And that means that the top of this building is not going to see as much load as the bottom. And again, that informs how we design buildings and where we choose to put assets, put the things that we're protecting, put the people that we're trying to protect, keep them down away from the bottom exterior and try to put them higher or further into the building. And this is an example of an explosion that occurred in Kabul in 2010. It was a hotel of some sort. The explosion occurred in the street, and it took out the structural elements on the side here. And close in, it was a complete collapse. But if you look at this photo here, as you get further away, it's the same construction of the buildings, but then you're not seeing any damage as you go further away. The distance and the angle of incidence have changed, so you have more protection just by where it's located. And those really, when you're looking at where to set your perimeters, where the perimeters are set, those are the types of things that can really change what's happening at the building. Again, even before you harden it. Confined explosions. So an explosion is a rapid release of energy and it goes outward in all directions. So it dissipates as it goes out. But if you are in a confined or semi-confined space, it's not dissipating. So it starts bouncing back and forth and you get reflections and refractions, and that increases the duration and it increases the load. So from a combined explosion, the same size charge, even if it's the same building construction, you will see more damage from a confined or semi-confined explosion than an open air explosion. This image on the left is from the 1993 World Trade Center bombing. A truck was parked in the parking garage and detonated, and you can see, so these are the columns, those very, very large box girders with, I think it was 4 to 6 inches of steel on each side. And what you can see here, these are actually the where the slabs used to be. And so this explosion, it went up and it hit slabs that aren't designed to be going up. So it failed those slabs and it went out in all directions. So this was a much longer duration than the same size threat that would have been in the open. And then just this one to the right is, when I talk about semi-confined, the explosion can go out to the left and the right, even the other side, but it's going to be semi-confined between this overhang and the wall and the ground itself. And that will increase, again, the magnitude, but it won't be as big as a fully confined location. So another thing that what I run into a lot is people want to put a blast wall up. And I kind of make the distinction between a blast wall and a shield wall. So what I think of a blast wall is, it's an actual physical concrete, whatever type of material wall that will not fail. It won't breach. It won't fall over. It won't bend and fail. That blast wall is designed to take that threat. And a shield wall, close in, it may fail a little bit, but as you get further away from the charge on that wall, it will stay intact. And it will be providing some sort of a shield, an interruption of the blast wave. But when you start looking at the calculations for it, it's a geometry game, 100%. It depends on the distance of your building to the wall, the charge to the other side of the wall, and also, the construction of the wall, etc. But really, it's this distance, it's the height of the building versus the height of the wall, and it's the distance on the other side. So what you find is, shield walls tend to have effect for close in or for near field explosions. And it will for buildings or people or different elements that are closer to the wall than far away. And when you have a far field explosion, it does very, very little. So I want to show you a couple of videos that kind of demonstrate that. So this is a test at the blast test facility, and explosion is to the right. It's super high speed, so we can see what's happening. This is that shock wave I was talking about before. It's going to hit the front of this structure. You're going to see a little turbulence. You can see some of the reflections, but then also if you look at the sides, you can see it affecting that door. And then you can also see on the back that there is load there. And then as it goes further away, it reconstitutes itself so that it's almost like that building, that edifice wasn't there. So there is a small portion of areas that can be shielded, but they're really not very much. And if you're counting on that to protect your facility or your compound or your building, you got to be darn sure that that threat is going to be located exactly where you think it is, because as you go further away, it doesn't do its job. So the other thing, this is a video from an explosion in Afghanistan, from a security camera on a protected building. So it happens out here. You can see the wave shooting over the land. This is a slow-mo. You can see it affecting things. Over here, you can see it. It's causing some damage, and the dirt and everything is being sent up into the air. But if you look one more time, there's no line of sight from where that detonation occurred to what's happening here. So just because the explosion can't see you doesn't mean that it's not going to affect. And I think that's a really important thing to remember when you're doing design, because just because my building is behind another building that potentially is taller doesn't mean I don't need to put protections into that second building. Oops, one more time. So then the consequences of explosions are, we've seen them on TV, we've seen them in photos, some of us have seen them in person. And the primary one is that we look at is injuries and fatalities. We also look at building damage and collapse. And really in our industry, when we talk about protection, we really talk about the building damage and collapse, and because that is our indicator of what injuries and fatalities will occur inside that building. So by focusing on the building itself, keeping it standing, reducing the amount of debris that is thrown, we're inherently protecting the people who are inside of that structure as well. So sometimes if when we start talking about it, we have to remember that really the goal is to protect the people 95% of the time. Other times it might be the asset, it might be information, it might be the continuity of the mission that's being required. And if it hits infrastructure, it's the interruption of infrastructure and how long it takes to get that, whatever that infrastructure was doing, whether it's power, whether it's water, whether it's a bridge or roadway, how long it takes to get that back up and running, in addition to the people who have been injured. And then, another one that people, it's not necessarily spoken about, but I think people are always thinking about it is the reputation. So, the larger explosions that have happened in the United States and elsewhere, a lot of times they're done on iconic structures. They're done on, highly populated areas. They're done on something that has a particular significance, because that gets the views, that gets the news crews are there. They're showing what's happening. There's sort of a 24/7 news cycle on it. And so, for instance, if it was a financial institution that was targeted, every single news is going to say this particular financial institution has been attacked. Here are the damages. And so it is a reputational thing as well. Definitely that is not more important than these other types of things that we just talked about, but it is still something to be put into the equation when you're thinking about how you want to protect a facility. So there's different types of damage, and there's really sort of breaking into structural damage, the damage to an actual element that's holding your building up, versus non-structural, which are your windows, your doors. It could be your overhead drop ceiling grid. It can be the lights that are in it. There's a lot of different types of non-structural damage, but just because it's not dropping the building doesn't mean it's not causing injuries. So they both have to be addressed when you're looking at it. So the types of damage that can occur from an explosion on the structural side, this one is our pictures from the 1998 embassy bombing in Nairobi. This was a high-rise bank building. This is the embassy itself, and this location right here, that used to be what's called the Untitled Cooperative House, which I think was a 6-story building that was had extensive damage, and not only just the initial damage, it had disproportionate or progressive collapse type damage. And that means that, something that happens in the front of a building, for instance, if it cascades all the way to the back, that is a disproportionate or progressive collapse. And so what you can see, so different types of construction are very important as well. The bank building, the explosion took place about here. So the Ufundi was closer than the bank building, but still it was very close to the bank building, and it was quite close to the embassy itself. But those were much more inherently robust types of construction. And this Ufundi Cooperative House was a more of a precast structure. So it's almost like a house of cards. So if you get rid of one and it's not designed to take that, they sort of kind of cascades or goes for progressive collapse. So, when you get into design or assessment of existing buildings, you have to look at not only the explosion things that we've spoken about, but you also have to look at what kind of structure, how robust is it? If you remove one portion, what happens to the rest of it? And those are in many of the guidelines that we use to design. This one is two photos from an interior explosion at a UN facility. And what happened was it was a facility, had a fence around it, but it had very long entry drive that were pretty much a straight shot to the structure itself. A vehicle was able to get through the perimeter and drove toward the building, actually got into the lobby and then detonated there. And these were some of the damage that occurred closer into it. And it's very significant structural damage. So it's actually had to be shored up. as they cleaned up and as they got people out. So very extensive structural damage, and didn't necessarily bring the building down, but it was definitely on its way to doing that. And there had to be significant repairs after it happened. So on the non-structural debris, there you can see what happens. So this particular photo was interior of the Nairobi embassy bombing, and you can just see this is all rubble. These are things that were in the room. You can see the drop ceiling grid here. These are things that fell out of it. It's some of the HVAC. It's everything that's up above you and often to the sides of you as well. And while that's not a building collapsing on you, it can cause significant injury and fatalities. So it has to be addressed when you're looking at how to protect buildings and people. This one here, actually, I can't remember where this one was, but this is sort of an outside exterior curtain wall, and you can see the damage to the glass, and glass tends to be the most fragile part of a building. So that's one of the first things that get protected against. And you can see that it broke as shards. So there's different types of glass, and annealed glass breaks like this. And that's the most hazardous in an explosion, because they're jagged pieces that are thrown into the room, potentially at people. And so when we do protection against windows, and I'll show you some on the next slide, this is what happens. And then also this was an airport bombing in Belgium, and these are the ceiling tiles and some of the structure, the portions of the building, non-structural, that were above. And this one's kind of sneaky because it's not actually an explosion. This is from the World Trade Center bombing in the lower levels, and but you can just see how it's affecting the utilities. And I always think it's really important for people to think about that, because if it's a mission critical and you have to continue operations, this is not going to help you continue operations. So you have to look at how to protect that. And then also, if people go in to get people out, to rescue, to clear debris, if these are sewer lines or electric lines, there's some hazard just from that there, the damage to those, whether it's biohazard sewage or whether it's hot electric. Just have to remember that those hazards exist. So this is windows and glazing. And these two, to the bottom right and the top left, those are actually protective windows. But in the case of this one on the upper left, it was actually a ballistic resistant window. And ballistic resistant windows are very robust. They're much thicker than blast resistant windows 90% of the time, and they're very heavy. So what happened here is they put this window in and it did the job. Ballistics, it would protect, as required, but it wasn't connected to the building structure enough to be able to keep it in place when an explosion happens. So it's a very different type, and ballistics is a very localized, very focused load, whereas the blast is the whole thing. And so the connections from the building to the window failed. This particular one happened on a Saturday, but if it happened on a work day, this was the chair of the person who was sitting next to it. So again, that's a very significant hazard when things are not designed and detailed for an explosion. This one to the lower right is a window that has anti-shatter, shatter resistant, blast resistant, also same names for film, that is designed to keep the shards together. There's two applications. One, if it's daylight, all it's doing is keeping the shards together. It does not make the glass stronger, but it reduces the throw and it reduces the jagged shards that can be thrown into a room, so it reduces the injuries. And then the other is if you attach it to the film, to the framing system, and then it actually does increase the strength. But these are both retrofit type applications. And in the upper right and lower left, these are windows and glazing systems that were not designed to resist explosions in any way. This one was from that Abuja explosion. You can see this panel, it fractured and was thrown in. And again, those are hazards. And this actually right here used to be a facade curtain wall. So that was completely gone. And these are the types of consequences from an explosion that we defend against. So I have 7 easy actions to take to increase safety. And I developed these when working with our clients who are in more hostile environments, and where there's probably a greater probability of explosions affecting their buildings. But quite frankly, I think they're really good, just sound design practices and housekeeping practices for all buildings that might be affected by an explosion. And the first thing is that I know everybody loves a window seat, and I got to tell you, I am looking out a ginormous window right now. So I am not practicing what I preach in any way. You really want to locate the desks and the chairs so they're not directly in front of a window, because again, the window is the most fragile portion of the building. So if the glass can break and fall on the desk, that's okay, but as long as it's not okay, but it's better than it falling directly on the person. And also, if possible, you don't want your doors in line, your desks or your people in line with doors either, because again, those are quite fragile in event of explosion, and they often get thrown into a building. So what we find also is that I've gone places where we've done all of this retrofit for the exterior wall to make it safe, to reduce the amount of shattering glass that might come in. But then the people who are occupying it have put pictures and other hard decorations on the exterior walls. So, your window might not fly in anymore, but everything that's been placed on the wall is going to fly in. So, if you put your decorations away from that wall, just by doing that, you're decreasing the potential for injury in an explosion. So in a lot of locations, where the bathrooms or the kitchen are on the exterior wall of a building, so they're on the perimeter right next to the outdoors. When there's wet locations, they often put tile onto the interior portion of those exterior walls, and those become little tiny projectiles or large projectiles. They're just going to pop off and they're going to fly. So again, we've done all this to protect the exterior walls of the buildings and the glass and the doors, but these tiles now become projectiles and they can injure people. So looking for other options for taking care of a wet environment, if you can do that, that really makes a lot of sense as well. And you don't want to install interior glass. Again, this whole thing goes to, we put effort into the outside, we're sort of creating this more secure envelope, but then all of a sudden I have a glass wall between me and the exterior. And that's an interior wall. So if the exterior window breaks, which it in some cases will, it's just going to come through and hit people with glass that hasn't protected on the inside. So you either don't want to put in those glass partitions, or you want to protect them the same way that you would an exterior window. And then you don't want to put, you put beautiful pictures up, and then you put glass in the picture frame. And that glass usually is that annealed glass, which is the most hazardous in the event of explosion. So, you know, if you're in a hostile environment, if you're on sort of the perimeter of a building, you know, maybe just use a piece of plexiglass in front of it, or maybe leave it with no glass at all. This goes back to, again, look, the bookcases, filing cabinets, a lot of times those are pushed against the outer wall. You think they're heavy, it's not going to be such a problem, but that blast load, when it flexes that wall, they are going to come in and they become hazards. And then finally, and this again, if you're in a seismic zone, if you are in a hurricane zone, if you're in a place where you might have explosions, take the basic seismic safety standards and attach your bookcases to the wall. You know, you have at the top, there's often little brackets or something that you install. Same with filing cabinets. If you have precious statuettes or anything like that, if you have something that's important to you, you can, if you put them in a bookcase, you can glue them down with museum putty. So it just keeps it in place a little bit more. But so everything that you can look at from sort of the furnishings perspective that you would do for seismic, it will help you in the event of an explosion as well. And that is the end of my presentation. I'm really looking forward to getting some questions. This right here is my contact details. I'm always available if somebody wants to talk something through, has a question, and I look forward to your questions. Thanks very much.
Okay,
Yeah.
Holly, thank you. That was awesome, really. We are going to switch things up today. Like I said, we're not going to have a panel discussion. We're just going to do Q&A. So everyone start asking your questions in the chat box at the screen, and we'll field them as we can. So go ahead and get that going. Also, just a quick reminder, near the end of this talk, we're going to send out a little questionnaire, a little survey that we'd love for you guys to fill out. So it will give us an idea of, you know, possible topics that we'll cover in the future, and give us a sense of really what you guys want to see. So it would be great if you'll just take a little bit of time to fill that out. That'll be cool. Thank you. Halls, I'm going to kick off with a question of my own, because here I am, a non-expert, but my takeaway from that presentation is, of all the critical things from my perspective, it's really standoff distance that is ultra important. Yeah, is
absolutely. So sometimes, you know, I think it through as in real estate, it's location, location, location. So in blast, it's standoff, standoff, standoff. The more standoff you can get, the less load that's getting applied to the building or your structure, and the more inherent protection provided by the structure, because it's not getting as much load. Right. It doesn't mean that you don't have to design or harden it, but it means that the amount of it, or the robustness of it, doesn't have to be as big if you have a standoff here versus one here. And that means that there is more money, your resources are able to be redeployed to other portions of the building, other functions of the building, right. Maybe more on the aesthetic side as well. So yeah, standoff is good. Standoff is critical.
Okay, one of our audience has a question. So the question goes something like this, and I quote, so all of these offices that have really sexy glass are actually endangering their occupants. Do you walk by them and kind of cringe sometimes, Holly?
So when I'm assessing buildings, I always cringe. However, I do have to own up to the fact that I used to work in a WeWork, and it's all glass. But yeah, if you're in a place that there is the potential for an explosion, you don't want to have those in there, as beautiful as they might be, or you protect them similar to what you would do on the exterior of the building.
Right. Okay. Okay. And now they're really coming in. So I'm gonna start
Okay.
firing questions at you. Get ready. This one is from Travis. Do you recommend in frame anchoring for glazing, or can external epoxy be adequate for energy absorption without a failure?
I'm not certain what you mean by the epoxy. So I'm going to sort of work through a window system. So the glass itself is attached to the frame. You can either have a dry glazed bite, which is sort of how much the glass goes into the frame. And those can be either you have dry glazed, or you have what's called structural silicone sealant, which allows you to have a smaller bite, but still get the same amount of grip. So you're keeping that window in place. Then the next thing is the frame has to be attached to the wall systems. If it's a new build and there's the ability to, for instance, if it's a concrete wall, if there's the ability to have embedded plates that are designed to take the force, that's what you would want to do. If it's a retrofit, you can use epoxy anchors, chemical type anchors that are for retrofits. And then if you can't do either of those, you can install steel behind the window and it goes to the floor and the ceiling. And but that's a really intrusive protection. And then in areas where time is of the essence, or where aesthetics are not quite as important, you can put cable catch systems behind that. So you assume that the window will come out of the frame, come out of the wall, but it'll be caught by these cables and it won't fly into the room. I don't think I answered the entire question, but ask it again if you need any more.
Yeah, we can probably pick it up and get in contact with them on email later on. Next question is from Ben Neal. The military used berms to deflect the blast upward and away from the building. How effective are berms?
They are effective. One of the things it's with shape. So for instance, if you have a concave shape where there's sort of an area that the blast can get captured, and then be directed up, it does do some of that, some protection from that. I'd have never seen any studies to see how much it would decrease, but I do know there's testing that's shown it. In fact, I know there's a wall system that's like a T-wall, but it's not. It's a T-wall with curve. It looks like a wave that you're surfing. Okay. And I know there's been testing on that, and that those have been deployed as well. So there is some redirection, but again, I don't think that these berms or these walls are going to stop it. It just might reduce it.
Right. Okay. Next question is from Wes. Are corrugated facades effective for breaking up blast waves and reducing damage, or are flat surfaces better?
I see what you mean. So if you're thinking like a corrugated metal deck type thing, something that's got some ins and outs, those actually are little areas to capture load. So it might stay there a little bit longer. So that's not necessarily, if you think of it that way, it's not necessarily going to decrease your load. But if you're thinking of the form of a building or the form of a wall, if you have a ball, like a golf ball without the rivets in it, divots, you have a round shape, you have an orb, again, reflected versus incidence, right? So when your blast load hits an orb or a ball, there's only a very, very small portion that's actually getting reflected pressure, right? Everything away from that is decreasing because the angle of incidence is changing. So the blast load effect on one of those types of buildings shapes would be significantly less. But if you have a U-shaped building, there would be more because it's capturing and it becomes a semi-confined blast as well.
Right. Interesting. Interesting. Okay. Next question from Jamie. Are structural protective measures similar for seismic threats as for blast threats?
Good question. So oddly, the basic premise of designing against either seismic or an above ground blast, they're in opposition to each other. So the basic premise is, so with a blast, and I have a heavy building or I have a heavy wall, before that wall can get damaged, it has to be put into motion. So the heavier it is, the more load it's going to take to start making it bend or to put it into motion. So heavy weight is really good from a blast perspective. On the seismic side, where the load is coming from the ground, so it's coming underneath the building. So as the seismic wave comes, it's going to hit the bottom of the building, and that's going to start moving. But if it's very heavy, the top part is going to not move as quickly. Essentially. And that is something that you really try to avoid in seismic design. You want to be able to have a lighter building from seismic, heavier from blast. But when you start getting into sort of more of the nitty gritty, the detailing, how you design and construct the connections between columns and beams, how you put your reinforcing into a concrete beam, all of that, those detailing elements start coming together, and one complements the other much of the time. Okay.
All right. There's a bunch of questions here. One of them is a sort of a standout from James. I'm going to answer that actually, that question. James is asking, is there any available info about drone-based threats? James, great question. And I've got not necessarily information for you yet, but PROTO-TALKS in January of next year will be covering that very topic for you. We have an outstanding guest speaker, as all of our guest speakers are outstanding. They're going to be here. They're going to be here in January. And so make sure you tune in to that, because I've seen bits and bobs of that presentation. It is absolutely fascinating. So I hope that answers your question.
And that I'm going to chime in. That's really important because, again, I talked about package bombs, suitcase bombs, there's vest bombs, there's all of that. So that the mode of transportation generally keeps to the bottom of a structure. So you don't necessarily protect the type.
Yeah.
So with the advent of these drones, it's really going to potentially change the design approach to these things. So that's really, I'm going to be really interested to see that as well.
Right. Okay. Paul is asking, are the walls/buildings also designed for rebound? Can you go more into detail regarding gash pressures? So I think that's a two-part question.
Yeah. So I'm going to go for the rebound one first. So there's sort of two. So, okay. You have the inward, this is my column, this is my blast load, this is the inbound load. But when you release load, often you get a rebound. If it stays elastic, it's like a rubber band versus a pencil. So that's rebound. And then there's a second portion that you look at if something coming out that brings it further out, and that's the negative phase, where I was saying, the blast goes forward, it creates basically a vacuum behind it. And then when the blast front is gone, it starts sucking things back in. So it's a negative phase. So there's different types of levels of protection when you would want to look at rebound and negative. When you're looking at the actual structure, so you're looking at columns, you're looking at supporting walls, you're looking at anything that's really holding the building up, then you really want to take a look at rebound and the negative phase. Because, just because it doesn't fail inward doesn't mean it won't fail outward, because not everything is symmetric when you're designing a column or a beam. So yeah, you would want to look at both. Times that you might not look at those things, and again, this is based on level of protection, but if you're allowed to let your glass break, you don't necessarily look at that because you're just really concerned about that inbound and what's happening. And if it gets sucked back out, that's not really what you are concerned about. And then infill walls. So, you have a frame and you have like masonry or something in between that space between the columns and the beams. That's an infill wall. Because they're not supporting the structure, they can fail in rebound in some cases. It depends, again, what the intent of the protection is. If you want to keep your building envelope intact and still functioning for all the other purposes, then you would look at rebound. But otherwise, if it's a lower level, you just look at that inbound load to it. So.
Right. I think in terms of getting more into pressures, we can get into a little bit later. This question from Abdel Amin, how do you decide what blast load to design to?
So there's sort of several portions to answer. When you're thinking about blast load, again, it's the threat size and it's where it can be located. So those two are important, but the question is, how do you get to that threat size? And then also, so yes, how do you get to that threat size? So it depends on the region that you're in. If you're designing in Iraq or Yemen versus designing in Mojave Desert, there's two hugely different threats, right? So the probability, the credibility of a threat is very different, as would be the credibility of the size of a threat. So often, again, we were talking about terrorists wanting to have a visual impact. They're making a statement. They want it to be very televised, or it's an iconic place, or it's a high profile tenant. They are probably going to put their resources against the really high profile instead of against a small outpost in a very suburban, very rural environment. That's not to say it's not going to happen. Maybe there's something critical happening in that location. But again, a threat assessment has to be done. And that's either done by the owner or by their security consultant, or, sometimes we help them think through what they're looking at. But it's one thing I think is very important at that is you don't necessarily want to look at the maximum credible size of threat as opposed to one maximum size versus a credible, because it's all about resources. If you are looking at a 30,000-pound bomb in a downtown area with very short standoff, A, you probably can't build it feasibly, but B, if you can't, all of those protective resources are going to have to be going against that. So there's a philosophical approach that the owner or the government has to think through. And then from that, we look at where that bomb can reach. So if we think we have a really good perimeter around our property, it would be, if it was a VBID, vehicle-borne IED, it would be at the exterior. If there's a parking garage and we think that the security is pretty good, we would probably put a smaller threat in there that might have gotten through security. But this is never done in a vacuum. It's really, when it comes down to it, it's the owner, it's the occupant, it's what their risk tolerance is, and it's about what the threat would be against them. Okay.
All right. Holly, you have so many questions here, it's ridiculous. But we're
can I do one thing? Because I know we're at 60 minutes and I'm very pleased to stay on, but I actually have a question for the audience. I know that we have some government folks, and I know we have some manufacturers on. And so I was speaking with a few colleagues last week, some in the government and some sort of on the design side of things. And they mentioned that we were having really severe challenges in finding specific products for blast. The organization that we're speaking with, it was more looking at historic preservation and how we can protect historic structures and not damage the historic nature of the structure or the fabric.
Okay.
But that's, they expanded it beyond that. They were all having problems with something. And they were, they asked why there weren't more products on the market, more unique products. And they asked what would be needed to expand what was out there. So my first take was that there's two things. One is that there needs to be some sort of R&D funding. But also the other thing is they need, in order for a manufacturer, in order for any of us to create a product, we need to know there's a need for it. We need to know that there's a market for it. So I have two questions for the audience on that, and you can put it in the chat and I can look at it later. You can send it to me via email. But I just wanted to know is from the manufacturer side, how do you decide on the new products that you're going to create? And then also, how do you find out what the needs are of these, I'm going to say government agencies, because they're our largest market, but how do you find out what their needs are? Is there a place that you go to get that information? Or, how does that happen? So I think that there's a hole in our community, in our industry right now. And I think it would be really interesting to figure out a way to bring it all together. So that they're a really good information transfer. But in order to do that, we need to know sort of where things stand now. So I would appreciate any thoughts on that.
Yeah, we could field that information as much as we can and get it to you also as well.
Yeah, no, absolutely.
Yeah, here's just a general question for me, because I'm fascinated by what you do. But when you step into a project, and whether it's a retrofit or a design or, well, I suppose those are actually two different questions in themselves. So I'll keep it more broad-based. When you step into a project, what sort of, when you're talking to your client, what's the first thing that you look at in terms of a building's current status of safety or protective design?
So if it's a new building, we start with, what are we designing against? What kind of threats do you have locations? So if it's a government agency, that's pretty well standardized for each different agency. So we can talk through what we're looking at. And we also always need to know what level of protection. So are you interested in, are you thinking that it's okay if a window breaks and comes into a room, as long as it doesn't fly too far and the shards are retained? Or do you require that those windows stay intact and don't even break? So those three things, it's what the threat sizes are, where the locations might be, parking garage, perimeter, are you worried about somebody bringing it into the building? And the third thing is actually the level of protection. So there's that for new construction, and it's a bit of that with existing buildings. But if we're going to do an assessment, what we generally do is gather information about the building, talk with the tenants, talk with the owners, and get a feel for what they're concerned about. But then we go back and do analysis and sort of come up with what threat sizes can it take now from these different locations, and what would be required to either increase that or increase the protection provided by the building. But it really has to all start with, do we know our threats? Do we know our locations? And do we know the level of protection?
Yeah. What are you designing against? What are you securing against? That kind of thing.
Yeah, exactly.
Okay, well, back to the audience. Are there any retrofits that can work with operable windows when locking them shut is not an option? Exclude catchment systems.
Okay, darn it. That was my first one. The retrofits, depends on how often you need to open them. So for instance, and in some situations from a maintenance perspective, you want to be able to get to your original window and be able to clean them, to make sure that they're all intact, that, you know, you do general maintenance. In those cases, one of the retrofits that we would use the most often is sort of an interior window system, secondary window system. So that can be removed or can be opened. But that particular window would be designed so if it's opened or if it's closed, it still resists the blast load. So that's one thing. Another thing would be if they are sliding type windows, we can look at reinforcing the verticals or the horizontals or whatever we have in the window, and then looking at that as it slides along. So if it's at a different places of being able to be opened, but those won't necessarily be pretty. And then the final thing would be, you know, there are some hardware type retrofits that can be installed. Again, if it has to be opened all the time, that's one type of thing. Or if it's just, you know, a maintenance type thing, we can do that as well. But yeah, so those are kind of the three things. And catch systems, usually with catchment systems, I know you didn't want them, but you can open a little. So if you're looking for fresh air, you know, or anything like that, there can be some air transfer. Important to remember, though, is that if a window is open, it's not stopping the blast load. So what we would be doing is making sure that the window fails in the way it's supposed to, but we're not able to do anything for blast load that's going in.
Right. Okay. All right. Next up, assuming blast load design can be sensitive information, can you share how you keep that sort of information protected when discussing and designing a project? Yeah.
So almost all projects, that is the sensitive information on the. So the most basic way that we do it is there are people who have to know what the actual charge sizes are. So that would generally be us and probably the owner or the agency or the occupant. And we can keep it a close hold for the actual size, like the actual pounds or whatever we're looking at. And then we would put a code on it, you know, and explosive weight 1, explosive weight 2, A, B, C, whatever that code is. And then we have, you know, the very few people have that code sheet so it doesn't get lost what was designed to. But then all reports, all discussions, everything that are, you know, shared with the design team with many people, it would all be based on those, you know, the codes that we would use. So that's one way of doing it. Well, and that is a way of doing it, but also in conjunction with that, you know, there's a lot of, especially right now, the government has put into effect very rigorous information security requirements for anything that has CUI, controlled unclassified information, or I don't know, controlled technical information, I think CTI. And that includes, there's only certain places you can store it. There's only certain ways that you can transmit it. There's a whole host of things with that. So, but just the basic is really that code, putting a code together. Okay.
We put out that survey, everyone. So please do fill it out if you've got the time. It will be really helpful for us. So I think I'm going to call it. And we've got one last question, Halls. And short of not hanging frames or wall tiles on the exterior walls, are there any, perhaps not easy, retrofitting options for existing structures?
Oh, there's a whole host. There's a lot of retrofits that we can use on existing structures. And it depends on what type of structure you have. You know, if it's a beam and column type building with an infill, we would protect the structural members. You can use, you know, you can add steel. You can use fiber reinforced polymers, which are specially designed, basically strips that can transfer technology from the seismic world, but they can increase the strength of columns. If it's if it's the non-structural wall, that infill, we can just put a catch system behind it and just catch it so it doesn't hurt the people inside, but it still fails outwards. We can, if it's a column structure and our beam just can't stand, the weight or the load, we can put in a new column, for instance, so we can decrease the length of it. There's a whole host of things that can be done for existing structures, but they do often, they can be intrusive and they can cost quite a bit of money, but there's a huge array.
Okay. All right. Holly, I think that's it for today. There are a host of other questions to the audience. We are going to send you emails respectively to your questions so we can get them all answered. We just don't have the time today. Holly, this has been great. This has been great. It's always great to see you. On behalf of Proto-Getic, we're so happy that you came. And also, everyone, I'd once again just like to say thank you to Habersham Metal Products for sponsoring today. We're very grateful for their participation as well. So that's it, folks. Please look for our emails announcing the next Proto Talks. I think there's a lot of exciting stuff coming up. Holly, again, thank you. And thank you all. We're going to sign off now.
I appreciate everybody's time. Thank you.
Bye-bye now.